Leonard Mlodinow last night admitted that at the inception of quantum mechanics in the 1920s, there was a lot of philosophical discussion, but he said that that's not true anymore. Actually, there has been a revival of the kind of philosophical discussion that took place at the inception of quantum mechanics, and to a very large extent, that's because of John Bell, about whom I'm going to talk a little bit this morning. You may know that in the 1920s there was a series of conferences called the Solvay Conference, where basically all the physicists in the world at that time who were interested in this stuff came together. That was probably about 50 or 60 people at the time, and hashed out what this new theory meant. And out of that kind of emerged two great opponents, friendly opponents, Niels Bohr and Albert Einstein. Albert Einstein, who was one of the founders of quantum theory, came to dislike intensely the kind of way that Niels Bohr and his colleagues assessed the theory, which came to be called the Copenhagen interpretation. Some call it called the orthodox interpretation of quantum mechanics. And during the Solvay conferences, Einstein and Bohr had a number of encounters where Einstein tried to show that quantum mechanics couldn't be true, quantum theory couldn't be true. And he basically was defeated in those debates with Bohr, in the sense that he admitted that Bohr was right and that quantum mechanics was correct. Bohr may have thought that he'd won, but it turns out that Einstein took another tack, and in 1935 published a paper in which, in a sense, the greatest critic of quantum mechanics pointed out something, a very puzzling feature of quantum mechanics that nobody else had noticed since its inception. And this was a paper called "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" And we believe it was actually written by Podolsky, because you notice there's no "the" as the second word, and Podolsky, being Polish, his native language doesn't have definite articles in it. So we figure Podolsky actually wrote the paper, but throughout you can see the spirit of Einstein in it. And what Einstein did was take a question that had been expounded by philosophers for millennia, which is what is the nature of reality, and come up with admittedly a narrow definition of reality, but one that could be tested. And what he said was, if without in any way disturbing a system, we can predict with certainty, i.e. probability unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. Now that's a lot of words, and in a minute we'll get to a specific example of what that means. He then went on to say that whatever the meaning assigned to the term complete, he's trying to argue that quantum mechanics is not complete, the following requirement for a complete theory seems to be a necessary one. Every element of the physical reality must have a counterpart in the physical theory. And then he went on to argue that this was not true of quantum mechanics, and therefore quantum is an incomplete theory. So here is the experiment, kind of a character of the experiment. This is a picture from our book. And what we have here, where that dot is an atom which emits two photons, two light particles. By the way, the idea of a light particle was Einstein's idea originally. And these photons go off in opposite directions. Here they're represented by sticks. That's not a quantum mechanical representation. It's just one, kind of to get you to visualize it. And these go off in opposite directions. And here are our two observers, Alice and Bob. And these are their detectors, polarizers, which basically detect whether or not a photon goes through. Now, the quantum mechanical description of this situation is actually that, like properties in quantum mechanics in general, these photons do not have the property of whether or not they're going to go through the polarizer before you measure them and see whether or not they go through. You don't know whether or not they're going to go through. As a matter of fact, the quantum mechanical description is you cannot know before you measure it. However, because these particles came from the same atom, we do know that whatever result you get on one polarizer, you will also get on the other. So if a photon goes through Alice's polarizer, it also goes through Bob's. If it doesn't go through Alice's, it doesn't go through Bob's. Well, Einstein argued as follows, and actually this particular way of thinking about the experiment was due to David Bohm. Thank you. Now I got two things to hold. Okay. This particular way of looking at the experiment was due to David Bohm. Einstein's argument was rather more convoluted and hard to understand. This is kind of simpler to visualize, and even more important, it's the way these experiments are done. Anyway, Einstein argued as follows. Alice can detect a photon, say, and she finds that her photon doesn't go through. Now, she knows, even if Bob isn't going to do it right away, if Bob's going to do it later, she knows what's going to happen to Bob's photon. So Alice says, oh, my photon went through. I know Bob's is. Therefore, Bob's photon has with certainty the property that it's going to go through Bob's polarizer. Therefore, by Einstein's definition, there is a physical reality to the property of that it's going to go, whatever property it is, it's actually called polarization, that it's going to go through Bob's polarizer. Therefore, that property is a real physical property of Bob's photon. Now, a critical argument is that since Alice and Bob could be very, very far apart, and something else that Einstein discovered, that nothing can travel faster than the speed of light, you can set up the experiment so there's nothing Alice can do that can affect Bob's photon. You just put them far enough apart. So she couldn't affect the photon, Bob's photon. And then Bob can't affect the photon before it gets to him. Therefore, she knows what's going to happen when the photon gets to Bob. Therefore, according to Einstein, it is a real physical property of the photon. Now, I told you that in the quantum theory, there is no such thing as the real polarization of the photon before it gets there. We say it's a superposition of possible states. Therefore, Einstein's argument is that there is an incompleteness to quantum theory. There's a real physical photon. Quantum theory doesn't deal with it. Therefore, quantum theory is incomplete. Now, and here's kind of, these are some quotes from Einstein's paper. For this purpose, let us suppose we have two systems, 1 and 2, which we permit to interact. That's basically the atom sending off the two systems here, the two photons. And again, on the other hand, since at the time of measurements the two systems can no longer interact, no real change can take place in the second system of consequence of anything that may be done to the first system, and that's because we can set it up so they're so far apart. Watertight argument, so it seemed. Well, the paper was published, it was sent to Bohr, he got it, he said it came down on him like a bolt in the blue. This was in 1935, and he stopped working on everything else, and he spent a furious 6 weeks, and he wrote an answer to Einstein. And he used exactly the same title, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? But he argued, yes, it is. And he argued it in the way Niels Bohr often argued it, in sort of a convoluted way, but let's see what he means. Of course, there is in a case like that just considered no question of a mechanical disturbance of the system under investigation during the last critical stage of the measuring procedure. Wow. Okay. What does he mean? He meant, well, I know, it's 30 years after Einstein published his paper on special relativity. We all know that that's correct. Therefore, it's true that nothing Alice can do can cause any kind of force, any kind of ordinary physical interaction to take place with the second system, because those things travel no faster than the speed of light. That's what he meant by mechanical disturbance. That included not just mechanical things, but electrical and so on. All the forces we know about in nature. Of course, we know, Einstein's right, that can't travel faster than the speed of light. But even at this stage, there is essentially the question of an influence on the very conditions which define the possible types of predictions regarding the future behavior of the system. Well, what does that mean? It means that something happens. Well, it's not a mechanical disturbance, it's not a force, but it's something. And he used the word influence, and that word has kind of become a catchword. It's the word we use to describe these weird kind of things. In other words, something happens to this particle when I observe this one. It's not a force. We call it an influence after Bohr. Something happens, somehow or other. When the two particles have interacted, what happens to one inevitably makes a change in the other. Well, Einstein thought that his arguments were going to stop physics in its tracks. Everybody was going to give up on quantum theory and figure out what the real theory had to be. While a brilliant physicist, he was a poor sociologist, and that's not what happened. People accepted what Bohr said, those people who bothered to read either of the papers, which was very few physicists at the time, and they just went on using quantum mechanics because in the 1930s, using quantum mechanics, scientists were able to analyze the properties of solids. They were able to probe the nucleus. Nuclear fission was discovered. Then, of course, World War II came along, and all the physicists went to work on radar or making atom bombs, and so on and so forth, and people paid no attention to this whatsoever. One problem was that physicists really like things to be settled by experiment. If you have a conflict, you want to be able to resolve it. And the problem with this experiment was that both Einstein and Bohr would give you the same experimental results. Einstein would say, well, there's some property not in quantum theory that causes these two particles to behave that way. Eventually, that property got to be called a hidden variable, hidden in the sense that it wasn't in quantum theory, whereas Bohr said, no, it's these influence, which Einstein called voodoo forces and spooky actions at a distance. He didn't like them at all. But they both said the experiment would give you the same result. So there was no way to resolve it except philosophically, and philosophy, Mlodinow was correct that for a while after the foundation of quantum theory, the interest in philosophy did die down for quite a while. Now, what revived it was John Bell's great idea. And Bell's great idea was, yes, it's true that Einstein and Bohr gave exactly the same result for the experiment when the polarizers were in the same direction. You may not have noticed that, but notice that both these devices called polarizers are pointing straight up. Bell thought, well, what would happen if one of them was turned? It turns out, while in this case, you notice they get exactly, one is going through, two is not, and you notice that the tapes which show what results they get are identical. On the other hand, if you turn one of the polarizers, some of the photons that go through Alice's polarizer will not go through Bob's polarizer and vice versa, and so you get some mismatches. Here's a couple right here where they get different results. And what Bell was able to do was to take Einstein's assumptions and come up with a mathematical equation governing the relationship between these two tapes, between the results of Alice and Bob. And we call the two, in a sense, we boil what Einstein idea down to two postulates, reality and locality. Reality says that there is a real physical property to the polarization of the photon, to the direction it's pointing. Locality says, is the assumption that nothing can travel faster than the speed of light, that what I do over here can't affect something over here at a rate faster than the speed of light. And with those two assumptions, he was able to come up with a mathematical equation representing the possible results. And here it is. This was published in 1964. And what these are basically correlations between different settings of the polarizers. And it doesn't really matter, what they are. But this is a mathematical relationship if Einstein's assumptions are correct. And these are experimental possible experimental results. These are things that you can do. Now, if you plug in the results, quantum mechanics predicts what PABC, PAB, and PAC are, and this is called Bell's inequality. And quantum mechanics, the results that quantum mechanics predicts violate this, as we would expect, because in quantum mechanics there is no reality until things are observed, and there is no locality. We have these spooky influences that Bohr talked about. So when Bell published this, he didn't think anybody would be able to actually do the experiments. They're quite tricky. But in the 1970s, a gentleman named Clauser, who was a postdoc at the University of California at Berkeley, actually did the experiments. He was hoping to get this result because that would overturn quantum theory and he'd get a Nobel Prize. Well, it turns out that the results that he got violated this inequality, and they were basically exactly what quantum theory predicted. And again, people didn't pay too much attention to this. But then in the 1980s, the experiments were repeated again with more sophisticated equipment by Alan Aspect and his team in France. And then people started to pick up and listen because we had duplication. You know, it's always an important thing in science, is to get duplication of results. Now here is the experimental test of Bell's inequalities using time-varying analyzers. And what this did was give a loophole in the experiment, because suppose you've got Alice's analyzer here and Bob's analyzer over here, and you might say, well, Alice and Bob's analyzers have been sitting here for a while. I know nothing can travel faster than the speed of light, but maybe something could travel to Bob's analyzer which would tell him the way Alice's analyzer was pointed, because they've been sitting here a long time. You know, we set them up, then we ran the experiment. What Alan Aspect did was use a system that could switch things so fast that essentially Bob didn't set his analyzer until after the atoms had left. So there was no way that any information about what happened at Alice's analyzer could communicate to Bob's analyzer. He actually was able to get the timing so that nothing really could travel. Nothing that happened here really could travel over there. And here's the results. The dotted line is the prediction of quantum mechanics. These are the experimental results. Here's the error bars. Notice that it fits perfectly. And this violates Bell's inequality. So, what's the result? The result is that Einstein's assumptions of reality and locality cannot both be correct, because the experimental result says that they're not correct. Because if they're correct, we get Bell's inequality, the experiments violate Bell's inequality, and what's correct? Quantum theory is correct. And here's what they say. Our observed violation of Bell's inequalities indicate that the experimental accuracy was good enough for pointing out a hypothetical discrepancy with predictions of quantum mechanics. No such effect was observed. Important point. Let us emphasize, this is in their paper, let us emphasize that such results cannot be taken as providing the possibility of faster than light communication. Something's traveling faster than the speed of light, but it's not communication, because standing over here, what does Bob see? He sees a series of ones and twos. What does Alice see? A series of ones and twos. It's not until they get together later and compare the results, or send a radio wave traveling at the speed of light and compare their results. It's not until then that they know what's going on and whether the results give something in agreement with quantum theory or not. All they ever see, though, is a series of, random ones and twos. So you cannot communicate with this, although people are trying to figure out how to do it, but nobody's come up with it yet. Now finally, just to bring us down to a little more mundane reality, you've heard talk about quantum computers, probably. Well, this is an example of a gate, which is a basic element of quantum computer, and this is actually about, what I think I say, the entire picture is about 1 centimeter across, so this is certainly visible. These are actually what are called superconducting Josephson junctions, and the connection between them is by this entanglement. And this is a quote from Science News, spooky action at a distance observed in superconductors big enough to be seen with the naked eye. So actually we have this kind of spooky stuff that Bruce was talking about happening in something that's really, you can see. Okay? So.
Please. Thank you.
Thank you.
So, again, just a couple of comments. All science is based on observation, experiment, theory.
Yes.
The observation and the experiment are the facts.
Correct.
But the theory is a story.
Yes.
And of course, the story then is invisible, right? It's not something that a fact is observable, but a story is the explanation in consciousness.
Well, also in books.
In books.
We write it down in textbooks, publish it in papers.
Okay. So what if you have a theory that says that the universe is acausally interrelated, that it's a single integrated activity, and it's a conscious universe? Then do you have these conundrums? Can you not explain these facts with a different story? And the story is, there are no cause-effect relationships. Everything is acausally interrelated. And it's a single activity. The universe is not a noun, it's a verb, and it's a single activity, and it's a conscious activity.
Well, I mean, that's a good story, and I could go along with it, but it doesn't explain anything.
It explains the facts. It explains your dilemma.
Well, the difference is that theories in science make very definite predictions, I mean, especially in physics, we get numerical predictions. Okay, while a good story, and as I said, you know, in general I like it, doesn't make any predictions that I can go and test in a laboratory and get me numerical results the way this kind of theory does. That's, you know,
yeah,
it's a different level of explanation.
Yeah. I think there's a problem then with science not understanding wholeness, you know, because all these stories are based on a reductionist thinking.
And it's been very successful.
Of course, it
but
has been successful.
No, well, I had a friend who used to say, science isn't everything and science isn't nothing. And I always liked that. You know, it made a lot of sense to me. Science is an important part of our way of grasping the world, and it's been very, very useful to us, and I think for me very satisfying in some areas, but it's not enough. It doesn't explain everything, and science in and of itself is not a satisfying worldview, I find. I think, and you know, so I would agree with you, you do need more than that. But I'm not sure that, to be honest, I'm not sure how much science points in a certain direction. And I think the quantum experiments point certainly toward the kind of thing you're talking about. I don't think it can get you there, but I think it points that way.
Okay. Thank you, sir.